Alive time, and today was a nice spring day, although brisk, but I'd like to welcome you to this spring's opening lecture for the Oceans Alive series. We'll be having talks for the next two Tuesdays after this week. Next week's talk is by Sandy McFarlane, who's a conservationist and an author, and she'll be talking about her new book, Rowing Forward, Looking Back. And the final presentation of the series this spring will be the science fair winners from Falmouth Academy and Falmouth High School, which is always a really inspiring evening to see how talented our young science students in the community are. But tonight, we have the pleasure of having Jeff Donnelly, who's an assistant scientist in Huey's Geology and Geophysics Department. And tonight, Jeff will be talking about chasing cyclones in coastal sediments. Jeff did his graduate work at Brown University, and he received some Sea Grant funding for some of that research that he had done out at the Museum of Natural History in looking at marsh sediments and reconstructing histories of marsh sediments in that region. But tonight he'll be talking about a lot of different aspects. So Jeff, without further ado.
Great. Thank you. Well, thanks for coming out tonight. I'm going to, like Judy said, talk a little bit about some of the research I've been doing over the last 7 or 8 years trying to reconstruct records of past hurricane activity. A little bit of an outline. First, I'm going to talk about why we might want to develop long-term records of hurricane activity. Also, talk a little bit about the conditions that are necessary for the formation of tropical cyclones, and also when and where they occur. Then I'll talk a little bit about the historic record, which is a pretty rich record for New England. And then I'll describe some of the methods that we use and present some of the results. And then finally, we can open it up for discussion. So why do we need to develop long-term records of hurricanes? Well, first, hurricanes cause a significant amount of damage and threaten lives all over the world, and particularly in the western Atlantic. This is particularly important because in the last 100 years or so, we've concentrated a lot of population and resources in that area that might be at risk. This is an aerial photograph taken just after Hurricane Carol in 1954 of a community, Oakland Beach in Narragansett Bay. And almost the entire community was destroyed in this particular storm. And actually, it had been destroyed a little over a decade earlier by the 1938 hurricane, and then rebuilt and then destroyed again. There's also ecological impacts, both terrestrial. You can see this is some forest damage from Hurricane Hugo in 1989. These are some mangroves that were destroyed in Hurricane Andrew in South Florida in 1992. And these are some fish in the Atchafalaya River in Louisiana that were impacted by Hurricane Andrew as well. We don't really have a good understanding for what governs the formation of hurricanes. We know some of the factors that seem to play a role, but we don't have a really good understanding of why they form, where they form, and then once they form, where they go. And due to the relatively short instrumental record, in terms of satellite data, we only have a few decades of information where we actually can see the storms from above. Prior to that, we were just relying on land-based records and ship records. So we have a very limited instrumental record. And the historic record, like I said earlier, goes back quite a ways in New England, just because it's been settled since the early 17th century. But in terms of having a good understanding for when these things occur, they're such rare events that even a 300-year record may only see one or two of these events. So it's important to get a longer-term perspective, and really that's what geology can provide. Here's a satellite image of Gloria, and like I mentioned, the satellite technology has only been available for a few decades. And finally, there's the potential for increases in the intensity and frequency of tropical cyclones due to global warming. Some models suggest that as the climate warms, sea surface temperatures will warm, and that will in turn cause more hurricanes and more intense hurricanes. And so it's really important to have a sense for whether these factors have contributed to increased cyclone activity in the past. I'm going to talk a little bit about just the 20th century and look at deaths and damage that resulted from hurricanes in that 100-year interval. You see the deaths pretty much have decreased exponentially through that century, with over 6,000 deaths in 1900. And that was actually the Galveston hurricane, Galveston, Texas in 1900. And you see that, particularly once we've gotten into the satellite age, we're really able to warn people and get them out of harm's way pretty well. On the other side of the coin, though, damage has gone up exponentially in that same interval, where we had very little damage and almost or over $30 billion in damage in the 1990s. And most of that was Hurricane Andrew in 1992. Now here's another graph that's essentially the same thing. This is just by year, and this really points out that 1992 event, Hurricane Andrew, with $30 billion in damage. Now Hurricane Andrew was bad for a couple reasons. One, it was a Category 5 hurricane. It's actually just been upgraded to a Category 5 recently. At the time of landfall, they thought it was a Category 4 hurricane, but they've kind of re-looked at the data and now think that it was actually a Category 5 hurricane. But it also had double landfall, in that it made landfall here in South Florida, traversed across the Gulf of Mexico, and made landfall again as a Category 4 hurricane in Louisiana. And here is some of the damage in South Florida, in Homestead, Florida, that resulted from Hurricane Andrew. So what if we look at this damage a different way? What if, if you looked at this, you might think that, wow, we're getting more hurricanes, more intense hurricanes, more damage. But if we take into account other things that have changed in that same time interval, and one of them is population. This is a graph of how population has changed in Barnstable County since 1900. You can see that we've gone from roughly 25,000 people to 225,000 people. So if we take that into effect, as well as the increase in wealth, not only do we have more people at the coast, but they have more stuff. We've got VCRs and cars and all sorts of things that are in harm's way. So if we take into account that increase in population and the increase in wealth in coastal areas at risk, we get a histogram more like this. So basically what this is looking at is, okay, what if these hurricanes that occurred in the past had occurred today? What would the damage have been? And if you do it that way, suddenly Andrew isn't the biggest event in that century. Really, the hurricane that would have caused the most damage if it were to have hit today was the 1926 Miami hurricane, which would have caused over $70 billion in damage. So in terms of where the resources are that are at risk, this is another histogram of coastal states all the way from the Gulf of Mexico through the Northeast, and the amount of insured coastal property in 1995 dollars. And you can see that about 1.8 trillion of the total 3.1 trillion actually is in the Northeast, where we got New York, Massachusetts, Connecticut, Maryland, New Jersey being some of the biggest. So now I want to talk a little bit about when they occur. This is a plot of the hurricane season, roughly running from June through November. And you can see that the peak in hurricane occurrence occurs in basically early September, but it starts to crank up here in late July and early August. And then basically, October, mid-October, it's pretty much tailing off. The red is both hurricanes and tropical storms, and the yellow is just hurricanes. Now I'm going to talk a little bit about where they occur, and this is basically the areas of formation in the early part of the season, in June, where you basically have the potential for development in the Gulf of Mexico. As you move to July, you still have the potential in the Gulf of Mexico, but things start to shift a little bit towards the Caribbean and the East Coast. And then we start to get into August, and that's when you're getting, it's starting to crank up, it's much more likely, and then the focus has shifted much more to the Caribbean. And then we move to September, the most active month, where basically you can get a hurricane to form anywhere in the western Atlantic and Gulf of Mexico. And then October, things kind of basically shift to just the eastern seaboard. And then things really start to tail off in November. So what are the conditions that are necessary for hurricane development? One is that you need warm sea surface temperatures. So sea surface temperatures that are around 80 degrees Fahrenheit. Another thing is you need minimal wind shear aloft, and that is you don't have very strong winds in the upper atmosphere that would essentially cut the top off of hurricanes as they started to form. And you need some sort of prior disturbance. So you need some sort of tropical wave or something coming off of Africa to really get things started. And you also need Coriolis deflection. So that means you need to be around 5 degrees north or south of the equator so that the effect of the Earth's rotation will give spin to the storm. I'm going to talk a little bit about El Nino, and this is a map of sea surface temperatures during an El Nino year, and this is South America, Central America, Australia. And so what El Nino really is a significant warming in the western tropical Pacific. And this is an anomaly map, so this is basically how much warmer it is than normal in this western tropical Pacific. In contrast, La Nina, which is the cold phase of El Nino, you can see that they basically have cold sea surface temperatures in the blue here in the western tropical Pacific. Well, why do I care about El Nino and La Nina? Well, it turns out that what phase you're in has a big impact on the tropical cyclone activity in the Atlantic. And the way it does that is via teleconnection. That warm sea surface temperature in the western Pacific actually changes the upper level winds in the Atlantic. And so basically you're getting a lot of that wind shear aloft and cutting the tops off the hurricanes before they even have a chance to form. This is the extent of the hurricane activity for 1983, a very strong El Nino year, where we just had a handful of tropical cyclones. By contrast, if we go to a strong La Nina year, this is 1995, you can see we've had quite a difference in hurricane activity. So what about future climate change? This is a record of CO2 from the Vostok ice core. There's actually CO2 gas preserved within the ice. And so you have a long-term record of what the concentration of CO2 in the atmosphere has been. And this goes back 160,000 years. And you can see it basically has fluctuated between about 200 and 300 parts per million. And this is kind of varying on glacial scales. And so you've got glaciers and then no glaciers and glaciers and no glaciers. This is about where we are today at 360 parts per million due to emissions from greenhouse gas emissions from fossil fuel use mostly. And then this is the projected level, the minimum projected level for where we're going to be in 2000 or 2100. And then this is the maximum based on the Intergovernmental Panel on Climate Change. And you can see that this is far and beyond anything that we've seen in the recent geologic past going back 160,000 years. And based on this, the IPCC is projecting 1 to 3.5 degrees warming relative to 1990 from that greenhouse effect. So if we look in the past, we can figure out how climate may have changed in the past. And these are some records that were developed from both ocean and terrestrial sediments. The top section here is sea surface temperature reconstructions from the Atlantic. And the top one here is off of West Africa. The black one in the middle here is from, actually that's the one from West Africa, sorry. The top one is from the Northeast Caribbean. And then the gray is from the Bermuda Rise. And you can see that this goes back roughly 2,000 years. And these were reconstructed from faunal records, looking at the forams, or the little bugs that were living in the water column, and looking at how those communities changed, and then how the chemical composition of those bugs are you're able to back out what the temperature of the sea surface was in the past. This bottom part of the graph is an El Nino record that was developed from southern Ecuador. I mean, basically each one of these increases in, they have red color intensity, but this is essentially a precipitation record. And so they've got a core where they're washing in material when it's typically dry during neutral or La Nina years, and during an El Nino year, you get a lot of precipitation, and you wash in this particular sediment with a redder color than the other sediments. And so they basically put together this proxy record of El Nino events, so that each one of these is a very strong El Nino. And you can see there's quite a bit of variability in El Nino over the last 2,000 years, where you've got intervals here with very few El Ninos, and then other intervals with quite a few. So now I'll talk a little bit about the historic record of hurricanes in the Northeast. And if we look at just the hurricanes in the 20th century, this is basically what we have. We've got a series of relatively weak Category 1 storms. Those are in the dashed lines here. The gray are Category 2 storms. And then the red is Category 3 storms. And really, we've only had one Category 3 storm in the 20th century, and that was the 1938 hurricane. The last hurricane to impact Cape Cod was Hurricane Bob here in 1991, which basically came right up over Newport, Rhode Island, and then out through southeastern Massachusetts. There's a satellite image of Bob just before it made landfall. When Bob made landfall at Newport, there was a fair amount of storm surge. And what storm surge is you have onshore winds, particularly on the east side of the hurricane as it's making landfall here in New England. So you've got it's a counterclockwise circulation, and so you've got onshore winds to the east of the hurricane. That's basically pushing up a wall of water up against the shore. And these are records of the water level changes at a variety of tide gauges. One right here in Woods Hole, another here in Newport, and another in New London. And you can see that they all have an increase about the same time. This dashed line here is actually when Bob made landfall in Newport, and that's it's where the storm surge peaks here, close to 1.5 meters above what would be the mean high water, or the normal high tide level. And actually, the most storm surge was in Woods Hole, which happened, roughly an hour later. And then, as the storm passes, the winds quickly switch to offshore, and the water level drops quite rapidly. Now, if we look at the Woods Hole tide gauge record and pick the top, roughly 12 storm surge events, the highest storm surge events in the 20th century, or at least since the tide gauge started recording in 1932, this is what we have. We've got the yellows are actually winter storms, and the reds are hurricane landfalls. So here's Bob here, roughly at 1.5 meters of storm surge. The next big event is Hurricane Carol in 1954. We've got the 44 hurricane, which was one of those Category 1 hurricanes. And then the big winner in the 20th century is the 1938 hurricane with over 2.5 meters of storm surge. Now, one of the things that occurs particularly in the Northeast is that the storms typically move pretty rapidly. And what that does is really gives you an asymmetric damage pattern, in that if you've got a storm that has winds of 100 miles an hour, circular winds here, moving around the center at 100 miles an hour, but the storm is moving at 40 miles an hour, you've basically got to subtract 40 miles an hour from the western side of the storm, where you're adding it to the eastern side of the storm. So what you actually feel on the ground is going to be 140 mile an hour winds, not 100 mile an hour winds. Now I'm going to show some reconstructions of the damage swath from some of these hurricanes. And these were done by Emory Booz at Harvard University. And what he's done is he's gone through the historic record, pulled out damage estimates, and then applied a kind of a simple model and generated these maps. And the maps, it's actually in the Fujita scale, which was actually first designed for tornadoes, but it's a damage classification. And so it works pretty well using it this way, trying to kind of reconstruct from the historic record. And so F0, the Fujita 0, is light damage with winds probably around 40 to 72 miles an hour. And F1 is moderate damage from 73 to 112. And then F2 is considerable damage, which is 113 to 157 miles an hour. And so the F2 would really be equivalent of a Category 3 hurricane in the Saffir-Simpson scale. And this is the reconstruction that he put together for Hurricane Carol in 1954. The hurricane, this is the track here. You can see that the damage swath is really off to the east. It's because that storm is moving at roughly 35 or 40 miles an hour. And so you're really accentuating the winds on the right side of the storm and taking away from the winds on the left side of the storm. This is downtown Providence, the Biltmore Hotel, just at the peak of the storm. And you see the entire downtown was flooded, up to about 10 or 12 feet on the city streets. The next storm was the 1944 hurricane, which again was a Category 1 hurricane when it made landfall in eastern Long Island. And you can see here again, you never really get any of this category, the equivalent of Category 3, the yellow here, anywhere near land. And it wasn't really that big of an event. Now if we look back, look here, we've got roughly 1.5 meters or so of storm surge here in Woods Hole. Then you see that the next one, the 1938 hurricane, was at basically over 2.5 meters of storm surge. And again, the 38 hurricane really just bisected Long Island and then moved up into Connecticut and up into northern New England as a Category 3 hurricane. Now this is a map that was generated by Al Redfield, actually, who the building is named after. And basically what he did was went and mapped out the storm surge related to the 1938 hurricane. And this is what that pattern looks like. And so you've got, this is the storm track here. And basically all the storm surge is to the east of the storm, to the storm center. And so here you've got 10 or 13 feet of storm surge. And if you look into the bays here, you actually get substantially more. So you get these basically funnel-shaped bays, and the storm surge really gets focused in those bays. And here we've got 15 or 17 feet of storm surge in some of these bays, and that's why we had so much flooding in Providence in both the 54 hurricane and the 38 hurricane. And here is the Biltmore Hotel again, with essentially that same scene where you've got 10 feet of water or so in the middle of Providence. And here's what that damage swath looks like from the Booz reconstruction. We got here the storm track, and you can see that we had F2 damage that went all the way up into northern New England. And that really just totally devastated most of the forest through central New England. Now prior to that, we also had an intense hurricane strike in the late 19th century. And in 1869, we had one that again just clipped the easternmost part of Long Island and then went into southern New England here. And see, again, we've got F2 damage that cuts a swath right across southeastern New England, or southeastern Massachusetts and Rhode Island. So if we look at the entire NOAA data set, the National Oceanic and Atmospheric Administration data set, that only goes back to 1851, there's really only two intense hurricanes that have made landfall, the 1938 hurricane and the 1869 hurricanes. There were a number of near misses, however. We've got 7 storms in that interval that came very perilously close to southern New England. Now, if we go back a little bit further, prior to when NOAA has a reliable data set, one of the storms in the historic interval that had the most significant impact on the Cape was the memorable October gale of 1841. And this storm didn't even make landfall, but just passed to the south of Nantucket, and was likely a Category 3 or potentially a Category 4 hurricane. And one thing that you notice here is that the storm was moving very slowly. It didn't accelerate like Hurricane Carol and the 1938 hurricane did. And because it wasn't moving very fast, the damage swath is much more symmetric. And the reason this was such a memorable gale is that most of the fishing fleet was out here, and there was substantial loss of life. There were 57 lives lost just in Truro alone, fishermen out at sea. If we go back a little bit further, there was another intense hurricane strike in 1815, very similar to the 1938 hurricane. Made landfall just a little bit further to the east on Long Island. And again, we've got this very large swath of F2 damage. And again, Providence. This is a painting of downtown Providence after the 1815 hurricane. There's a little artistic license here, I'm sure, but certainly we've got the same thing going on where we flooded the entire downtown of Providence. Now, the first record we have of an intense hurricane strike actually comes from very early in the historic interval. The 1635 hurricane, which is just 15 years after the Pilgrims arrived, cut a swath right across southeastern New England. And we have really good accounts here because the storm just happened to pass between Plymouth and Boston, where the two major settlements were at the time. And so there were a lot of people there, including the governors of both those colonies, that made pretty good notes. William Bradford from Plymouth said it caused the sea to swell to the south wind of this place above 20 feet right up and down, and made many of the Indians climb into trees for their safety. Now, in terms of just south wind of this place, just south of Plymouth, is probably most likely Wareham, right at the head of Buzzards Bay, where you get that focusing of the storm surge. And so there was roughly 20 feet of storm surge in Wareham, most likely. And it also goes on to say it blew down many hundreds of thousands of trees, turning up the stronger by the roots and breaking the higher pine trees off in the middle. And then John Winthrop from the Massachusetts Bay Colony talked about the storm surge in Narragansett, most likely Narragansett Bay, being 14 feet higher than ordinary and drowning 8 Indians. Well, what can the geologic record tell us about past hurricane activity? Again, here's the storm surge pattern from the 1938 hurricane. It's really this storm surge that gives us a mechanism to have a geologic record. Basically, this storm surge of 12 to 20 feet in some cases, it's really modifying the coastal zone. The combination of this storm surge and the waves on top of that storm surge are really modifying the coastal zone. And if we look at some aerial photographs taken immediately after the 1938 hurricane, what we see is that substantial overwash fans have been deposited in the back barrier environment. So this is Fire Island, New York. Here's the barrier beach. This is the Atlantic Ocean. These are actually foundations, and these are pieces of houses. The storm surge came up over the barrier and deposited these large lobes of sand into this back barrier salt marsh. The same is true here in Green Hill, Rhode Island, where all of this here is a big sheet overwash deposit that's deposited in the back barrier marsh. And then the same is true here in Charlestown, Rhode Island. And then this is at Watch Hill, Rhode Island, right at the Connecticut border, where this beach has been overtopped, and we've deposited these large overwash fans, in this case into a Little Narragansett Bay. And so that sedimentary deposition combined with sea level rise really provides a way of preserving that record. And this is a sea level curve generated from Cape Cod. And so what we've got here is time on this axis. So we're going back 10,000 years. And then this is depth below modern mean high water, the modern high tide mark here in meters. And so this is how sea level has changed in Cape Cod in the last 10,000 years, where it was changing very quickly here, started to slow, but it's been continuously rising through that interval. And what that means is that these marshes have been accumulating through time, keeping up with that sea level rise. And so this is a cross-section of a barrier island sequence where we've got the ocean side here. This is the modern barrier, the modern back barrier marsh, the modern back barrier lagoon, and then this is the upland. And so we're just kind of cutting a cross-section right through this. And what's happened through time is sea level's been rising, and this marsh has had to keep accumulating vertically in order to keep up with that sea level rise. But at the same time, episodically, storm surge is coming overtopping this barrier and depositing these large lenses of sand in the back barrier environment, causing this barrier to actually migrate landward with time. And so we can use this accumulation to reconstruct past occurrences of these overwashes. And the way we do that is just take a series of sediment cores behind the beach and basically map out these overwash fans, try to date them, and come up with a record of past storm surge. The way we get the sediment is to take sediment cores. This is a vibrocoring operation that we did up in Wareham. This is the beach at Little Harbor, and then this is the back barrier salt marsh. And you can see that in order for any of the sand from the beach on the other side of this to get back in here, you've got to overtop this barrier. And this barrier is roughly 2 meters high. So you've got to get storm surge over 2 meters to get the sand into this normally very quiescent environment that just has very fine-grained sediment. And so the vibrocore rig, got a small 5 horsepower motor here, actually vibrates this clamp, which in turn vibrates this tube into the mud. And it's basically liquefying the outer millimeter or so of sediment, allowing the tube to pass through it. And then using that tripod, we extract the tube and have a sediment core that can be as much as 30 or 40 feet long. Now these are some of the marsh cross sections from across the region. Here's that same site, Little Harbor, just the upper 20 centimeters or so. There's a sand layer here at about 3 centimeters, which dates to 1991 or Hurricane Bob. There's another one here at roughly 12 centimeters, which dates to 1954 or Hurricane Carol. And there's one right below that that dates to 1938. The same is true here in, this is a site in southern Rhode Island where this sand layer here actually dates to the 54 hurricane, and this one dates to the 1938 hurricane. And the same is true here. This is another site that I'll talk about today. This is actually a cross-section that we dug in the edge of the marsh, and you can see these sand layers all the way across the marsh that date to 1954 and 1938. So the first place I'm going to talk about is Succotash, which is here in southern Rhode Island, just next to Narragansett Bay. This is an aerial photograph of the site. So again, here we have that barrier beach, and then this is the back barrier salt marsh and some lagoon and some abandoned channels. If we look at the storm surge record for southern Rhode Island, you basically have The yellows, again, are winter storms. So winter storms are giving you, roughly, the most severe winter storms are giving you roughly 2 meters or so of storm surge. And then the red are the hurricanes again. And, a hurricane, a weak hurricane like Bob or Gloria or Donna, giving you 1 to 2 meters of storm surge. And then Hurricane Carol was over 3 meters. 1938 hurricane, again, over 3 meters. That 1869 hurricane that I talked about was roughly 2.5 meters. And then the 1815 hurricane was about 3.5. And then that 1635 was over 4 meters. This is an aerial photograph before and after Hurricane Carol at Succotash Marsh. Again, here's the beach. Here's the marsh behind it. You see, these are all cars lined up at the beach enjoying a nice hot summer day. There's a large cottage community here, another cottage community here. This is what that same area looked like immediately following Hurricane Carol. This is that same road. This is where those cars were parked. We basically overtopped the entire barrier. The cottage community is entirely washed away. These are the telephone poles here. And you basically deposited this layer of sand into the back barrier marsh. Now here's a map that we did and basically outlined the visible overwash sand from the 1954 hurricane and the 1938 hurricane. And the green here is that 1954 overwash that we were just looking at, and the red is the 1938 overwash. And what we did was took a series of sediment cores along these transects. And so we took that vibrocore rig out and just took a whole series of sediment cores. Here's what some of those sediment cores look like, at least down to 50 centimeters or so, where the dark areas are salt marsh peat, and that's what's depositing there today and depositing there every day, very slowly through time. The light layers are these overwash sands. So this is basically fine to medium sand that was deposited in these large fans across the marsh. If we put together a cross-section of what one of those transects looked like, it looks like this, where we have these basically continuous sand layers deposited across the marsh. And then the basal sediments here are actually a combination of sands, fine-grained laminae, and coarse-grained lag deposits from when there was a flood tidal delta complex here prior to when the marsh actually formed. So the record of overwash when the marsh really began to form is really truncated here at about a meter or so. And so we basically identified 6 different overwash fans at this particular site. And then the challenge was, okay, well, how do we date these fans? This is a cross-section of one of the cores, or the top of one of the cores from Succotash Marsh. And one of the methods that we used was to look at cesium-137. And cesium-137 is a byproduct of atmospheric nuclear weapons testing. And so when they started exploding nuclear weapons in the atmosphere in the early 1950s, cesium-137 started to rain out all over the world, and it's actually preserved within the marsh sediments. And so where we see the first arrival of cesium-137, we know that dates to roughly 1954. And then the peak in cesium and the peak in nuclear weapons testing occurred in 1963. And so by looking at the activity of cesium-137 in the sediments, we can basically assign 2 ages. We know where 1954 is, and we know where 1963 is. And if we look here at the top overwash fan, fan 6, it basically occurs right where we get the initial jump in cesium-137, which puts it right at 1954, which is consistent with that aerial photograph of it being deposited during Carol in that year. And then right below that, just a decade or so before, we have another fan which we think is deposited during the 1938 hurricane. In order to date some of the earlier deposits, we used a variety of techniques. One is radiocarbon, in that we can actually take some of the organic material from the marsh sediment, some of that fossil grass that's in there, which when it was living absorbed radiocarbon from the atmosphere. And once it died, that radiocarbon started decaying. And so based on how much of that radiocarbon is left, we can calculate how old that particular piece of grass is. And so we dated several of those samples right below these overwash fans, and gave us dates of roughly in the, this one, it gives you multiple ranges because there's the fluctuation or the amount of radiocarbon in the atmosphere hasn't remained constant with time. If it was, it'd be a pretty straightforward calculation, but because the concentration is varied in time, particularly in the historic interval when we were starting to burn fossil fuels and putting dead carbon into the atmosphere and basically diluting the radiocarbon in the atmosphere, we actually can get multiple ranges from the radiocarbon dates. But basically this particular range is telling us that this sample was either from 1931 to 1947, 1645 to 1682, or 1734 to 1806. And then this one, 1518, 1595, 1621 to 1662. And then this one just had one range from 1404 to 1446. What we can do is apply other techniques to help narrow that field. And one of the ways we do it is to look at metal pollution. And that's what this red histogram is here. These are lead concentrations within these organic sediments. And so what we're looking for here is we know that in the Industrial Revolution we started putting all sorts of heavy metals into the atmosphere by burning fossil fuels. And that's preserved within the marsh sediments. And so here we can see that we get a big rise in the metal pollution in the marsh sediments between this organic interval and that organic interval. And we know that's roughly somewhere between 1850 and 1900 AD. And so if that's the case, then we know that this interval is too young and this interval is too old. So the most likely age, or we can say that this interval is too young. We can say that this interval is too old because we're also looking at pollen data. And one thing that pollen can tell us is how the vegetation on the landscape has changed. And what we know is that Europeans came to New England, and within 50 years or so, it basically cleared the entire landscape. And that suddenly you'd gone over to European-style agriculture from what before was more virgin forest kind of thing. And there's a very pronounced signature of that in the pollen record. So in these organic sediments, we can look at the individual pollen grains and count them and figure out what the vegetation in the landscape was. And what we have here is rumex pollen, which is a weed. And what happens is when the Europeans cleared the landscape, weeds take over, and you get a substantial rise in the weed pollen within the sediments. And that occurs roughly in this interval here. And so we know that this interval is right when the Europeans have cleared the landscape, which is roughly about 1700 AD. So we know that this 1645 to 1682 range is probably too old. So it basically gives us a range of 1734 to 1806. And then the same can be used to narrow some of the other ranges. So it's basically we're kind of throwing every technique we can think of at this to try to narrow the range of the age of these particular overwash sediments. And what we came up with was this, is that again we got the upper one was Hurricane Carol in 1954. The one directly below that is again consistent with that aerial photography. It was probably in 1938. We have one that dates to the early 19th century, which is probably that 1815 hurricane. We've got one that dates to the early 17th century, which is probably the 1635 hurricane. And we also have two older deposits which date between 1411 and 1446 and 1295 to 1407. I'm going to skip kind of real quickly through some other sites that we've looked at. We're going to move to Barn Island, right on the Rhode Island-Connecticut border. It's a little bit different system in that it's not a back barrier marsh, and that the marsh is right behind the barrier. The marsh is right here, and the barrier is actually offshore. And this breach through the barrier, this used to be continuous here. This breach occurred in 1938 and has maintained an inlet there to present day. And so what we did was, zooming in on that particular part of the marsh there, we went in and took a whole series of those vibrocores across that marsh. And again, this is what the a cross-section at that marsh edge looks like. We've got these thin sand lenses deposited across the whole marsh. So it's a little bit different system in that we don't have the sediment source isn't right next to the marsh, but it's offshore. And actually this edge is actually eroding back, and so there's a nice scarp there. So that's why we were able to go and just clean off that scarp and look at those sand layers in cross-section very easily. So what we did again was take a whole series of cores and went through the same dating methodology, basically using the metals, using the cesium, using radiocarbon, using pollen. Here's a couple of those cores and some of those sand layers that were recovered in the cores. And this is kind of a idealized cross-section for that marsh. And basically this is what we came up with here. Now we've got a deposit that dates again to 1954, another one right before it that's probably 1938. Here we have something that dates to the late 19th century, which we think is this 1869 hurricane. Again, something that dates to the early 19th century, which we think is 1815. We think we have the 1635 recorded there as well. And here we have 3 prehistoric sand layers dating all the way back to roughly 1000 AD, the oldest one. I'm going to quickly move a little closer to home at Little Sippawisset Marsh here in Falmouth. So here we are in eastern Buzzards Bay, just north of Woods Hole. This is an aerial photograph of the marsh. I'm going to show just one core, one of many that we took from that particular marsh. Again, it's about 1.5 meters long. Again, a whole series of overwash deposits in there. Kind of cut to the chase. We did the same kind of dating here. We got something at the top, which we think is Hurricane Bob. Again, we have Carroll, 38, 1869, 1815, 1635, and then 3 prehistoric overwash fans dating back again to a little over 1,000 years ago. So we've kind of put together the whole region using these kind of idealized cores from each of those sites. We kind of tentatively anyway draw some correlations across these different sites, and that we certainly have sand layers that date to the same interval. The problem is that with radiocarbon methods I can only say, well, it was sometime in the 12th century or the 13th century. I can't narrow it down to a specific year or even decade, but they're at least consistent with one another. And then as we move to Little Sippawisset, the record got even a little longer, well over 1,000 years. So in summary, we've had at least 10 landfalling hurricanes that have significantly impacted southeastern New England and Cape Cod in the last 1,000 years or so. The sediment record indicates that there's a series of prehistoric hurricanes hit in the 9th, 11th, 13th, and 14th centuries. Cape Cod has not experienced a direct strike by an intense hurricane, though, since 1635. So all of these storms in the historic interval that did deposit these overwash fans struck much further to the west. It wasn't, or only the 1635 storm actually, the damage swath actually cut across Cape Cod itself. The storm surge associated with these intense landfalling hurricanes to the west have typically resulted in 3 to 4 meters of storm surge on the open coast, and in some cases over 5 meters of storm surge at the head of Buzzards Bay. And one lesson we kind of learned by looking at the historic record is that the hurricane doesn't necessarily have to make landfall in order to significantly impact the Cape. For instance, that memorable gale of 1841 passed to the south of the Cape, but it was moving so slow that you really got a big northeast component on the north side of the storm. And so Cape Cod was really significantly impacted by that particular event. So I've got a little bit of information here for if you're interested in doing some further reading or some references. And if you've got any interest in preparing for the next big one, there's a website there. Thanks for your attention.
Yep.
Is there
Mm-hmm.
These other ones, I mean, where KO ever did his work on Western Pond, the salt ponds, so forth, they've done as far as well.
Yep, absolutely.
And I take it that that was one time was a real barrier to future one.
Yep, absolutely. And in that book that KO did, there were a number of sand layers in there that he attributed to storms. I haven't done too much work in those ponds to date, mostly because they're a little complex. And one of the things that KO showed was that there's a lot of inlet dynamics going on there. And so that's really, you get an inlet that forms during a storm, and then suddenly you don't need to overtop a barrier to get sand washed into the back barrier. You're actually bringing them in on each tidal cycle kind of thing. But there's certainly a sediment record there, and that could be exploited, although it might be a little more complex. I've got a sediment core that I actually brought in for kind of show and tell. If people are interested after, we can take the plastic off and smell the nice marsh mud. Yeah?
Can you translate sand composition, sand layering to velocities?
And you can. It takes a certain velocity to transport a certain grain size, for instance. But much of what we see preserved is much more a function of what was available to the storm. So there is some sorting that goes on during the storm surge event, but it really more depends on what size grains were there to begin with. And if we look at the grain size distribution in these overwash fans, what we basically see is that there's a kind of a fining landward, and that the coarser material is getting left behind first, and the finer stuff is falling out later. But I mean, if you, at first glance, it looks like you've got a bigger storm like the 38 hurricane relative to Hurricane Carol seems to leave thicker layers. But again, that's going to be very dependent on local conditions and the aspect of the waves hitting that particular section of beach and the sediment supply. And so, general rule: bigger storms leave bigger sand layers, but it's not always the case. Anything else?
How did you determine the tracks for the earlier storms?
For the earlier historic storms? Well, for instance, the one that's the most difficult to constrain is that 1635 event. And like I said, we have a really good constraint on where it passed between Plymouth and Boston, because there were people there noting down how the wind direction changed. And so you take all those accounts, put them together, and you know that the storm had to have passed between those 2 points. The rest of that track is speculation for the most part, except now I think that we're starting to see that deposit in some of these marshes helps us constrain the track. And that, okay, I would argue that it looks like we've got that deposit or a deposit from that storm in all those sites, so therefore it's most likely that storm made landfall to the west of those sites. And so really that's all we have to constrain the track that far back.
And you can tell something about the intensity of the storm.
Right, by the extent of the overwash fans in terms of multiple sites. If I were to go to one site, find a sand layer, but then go to 10 others and not find it, it had to be a very localized event. It might have been a small Category 1 hurricane that made landfall right there. But what we've seen for these big hurricanes is that the storm surge event is a region-wide phenomenon. It goes from Long Island to Cape Cod, and it's really overtopping just about every barrier along that coast. And so it's a real widespread phenomenon. Yeah. Anything else? Yeah.
The weather patterns we've been experiencing over the last few months, and the existence of El Nino on the sea, is there any way to tell or suspect what it might be like because the hurricane seems to be coming up?
Yeah, well, there's a lot of people that make their living doing that. I'm not one of them. Typically, if we were in an El Nino situation, the Atlantic is going to be pretty quiet. I think this El Nino is kind of waning, and so if by the summer we're kind of in a neutral condition, it may be more of an average year in terms of hurricane landfall. But that's about as far as I'm willing to go. Projecting the future, I'm better at going in the past. Anything else? Yeah.
The North Shore marshes, Massachusetts, like produce the same results as far as the storms?
I think so. Some of the marshes that I've cored up there certainly have sand layers. The reason I didn't sample those for this particular study is because things would be much more complex because of the northeast storms. You also see something like that 1841 hurricane essentially acts like a nor'easter, in that if the storm's off to the south, your wind is coming from the northeast. And so you kind of, on the northeast facing coast, you probably have a mix of both strong nor'easters and hurricanes.
That's not the book, Gale.
What's that?
That's not the book.
No, no. Portland Gale was 1890 something. Yeah, yeah. Anything else? Steve.
Your records also back 1,000 years. Is there a possibility we push records back farther than that?
I think so. You know, am I going to be able to get back 4,000 years? Probably not. And the reason is that the whole shoreline's moving because of sea level rise. The first 1,000 years was pretty easy to get. We might get back 2,000 years by actually coring in what are modern day marshes. If we go a little further offshore, you may actually be able to core through and get to older marsh deposits that are preserved offshore. It's a little more difficult an undertaking than walking out into the marsh, but the potential is there to extend it back even further. There's another question? Yeah.
When you look at those sort of line graphs,
Mm-hmm.
you might cross, you associating, say, on this left one, was much wider and sort of down.
Oh, when I was doing the regional cores?
Yeah.
Yeah, right.
So that means that the average sediment layer faster is created.
Mm-hmm. Mm-hmm. Right.
And so you can also estimate from that, you know, what the sediment rate is.
Right.
In these different places.
Right.
Are there any reasons for the difference?
The differences? Well, the question is, when I showed the kind of regional synthesis where I had all different sites and was correlating across from different sites, some of them are at different depths. There's a variety of things that could cause that. One is that the sediments just accrete differently. In that, you know, one site, the sediment may accumulate faster than it did at some other site. Another thing is that these storm layers aren't really passive events. So they come through and they can actually erode some of the sediment. And then it could take, if there's a big thick layer that was deposited there, it could take decades before that gets revegetated and peat to get to form on top of it. Another thing that's going on there that could potentially offset the elevations is that there's some compaction that occurs when we do coring. So one core might have been compacted a little more than another core kind of thing, which, you know, gives you some offsets. In general, they're pretty close. And there's also, you know, there's just topography in the marsh as well, where it's probably, you know, 10 or 20 centimeters worth of topography in the marsh, which would also give you some offsets. So. Anything else? Great. Thanks again. Feel free to come up and smell the mud.